Graphical representation of inverse functions. Hello everyone. Let's begin our session on the graphical representation of inverse functions. To start, let's quickly recap where we left off. In our previous subsections, we focused on the algebraic side of things. We discussed the strict requirements a function must meet to have an inverse, specifically that the function must be bijective. As you recall, for a function to be bijective, it must be both one-to-one and onto. Now that we have the algebraic foundation settled, we are going to shift our focus from equations to visuals. In this section, we will explore how this inverse relationship is actually represented and visualized on a Cartesian plane. It is important that you pay close attention to these graphical properties. Understanding the visual nature of inverse functions is absolutely crucial because it will allow you to visualize the principal value branch when we move on to inverse trigonometric functions later in the lesson. This will make those complex concepts much more intuitive. The fundamental concept, swapping coordinates. Now that we have established the algebraic requirements for a function to have an inverse, let us move on to how this works visually. At its core, an inverse function, denoted as f inverse, simply reverses the operation of the original function, f. To understand this, consider the flow of the function. If the original function f takes an input x and produces an output y, we write this as y equals f of x. The inverse function, f inverse, performs the opposite action. It takes that output y and maps it back to the original input x mathematically. We represent this as x equals f inverse of y. This relationship gives rise to what we call the coordinate rule. This rule states that if a point with coordinates a comma b lies on the graph of the function f, then the point with coordinates b comma a must lie on the graph of its inverse function, f inverse. This simple swap of the x-coordinate and the y-coordinate is the foundation of the inverse graph. Once you grasp this concept of swapping coordinates, it becomes much easier to derive the actual graph, which is what we will cover in the next section. Step-by-step guide to deriving the inverse graph. Now that we understand the core concept of swapping coordinates, let's walk through a practical, step-by-step guide on how to actually derive the graph of an inverse function from a given original function. First, in step 1, we begin by plotting the original function, f of x. It is crucial here to draw the graph only within its restricted domain. As we discussed in the previous slides, the function must be bijective, meaning both one-to-one and onto to have an inverse. For example, if we are dealing with the sine function, we do not plot the entire wave. Instead, we only plot the specific portion from negative pi over 2 to pi over 2. Once the original curve is set, we move to step 2, drawing the identity line. This is the line y equals x, plotted on the same coordinate plane. For now, simply think of this line as a mirror, a concept we will examine more closely in the next slide. Step 3 is where we apply the coordinate rule we just learned. We identify several key points, x, y, on the graph of our original function and swap their values to obtain the points y, x to illustrate this. If the point pi over 2, 1 is on the graph of the sine function, then the point 1, pi over 2 must be on the graph of the inverse sine function. Finally, in step 4, we connect these new points with a smooth curve. While drawing this, ensure you maintain the same curvature as the original function, but keep in mind that the curve is now oriented along the new axes. Geometric interpretation, reflection across y equals x $. Now that we have walked through the step-by-step process of swapping coordinates, let us examine the geometric significance of that action. This process of interchanging the x and y coordinates is known as a reflection. Specifically, the graph of the inverse function, f inverse, is the mirror image of the original function, f, reflected across the diagonal line y equals x. To help you visualize this, imagine you have your graph plotted on a piece of paper. If you were to fold that paper exactly along the line y equals x, you would find that the curve of the original function lies perfectly on top of the curve of its inverse function. To make this concept even more intuitive, let us use a real-world analogy. Imagine you are standing in front of a mirror. In this scenario, the mirror represents the line y equals x. Your actual physical position relative to the mirror represents the original function, f, while your reflection in the glass represents the inverse function, f inverse. Just as the distance from you to the mirror is exactly the same as the distance from the mirror to your reflection, the distance from any point on the original function to the line y equals x is identical to the distance from that line to the corresponding point on the inverse function. Understanding this symmetry is key, as it allows us to sketch inverse graphs without having to calculate every single point. In the next slide, we will apply this geometric principle to a concrete example using the sine function. Illustrative example: \sin x dollar and \sin -1 x dollar. Now that we have discussed the theoretical steps and the geometric concept of reflection, let us put everything into practice with a concrete example. We will apply these steps to the sine function, specifically restricted to the domain from -π/2 to π/2. As we mentioned earlier, this restriction is essential to ensure the function is bijective, allowing it to have a valid inverse. First, let's look at step 1. Identifying points on the original function, f of x equals sine of x within our restricted domain, we can identify 3 primary points that define the shape of the curve: -π/2, -1, 0, 0, and π/2, 1. Moving to step 2, we apply the coordinate rule we discussed in the previous slides to find the points for the inverse function. F inverse of x equals inverse sine of x. By simply interchanging the x and y values of our previous points, we get -1, -π/2, 0, 0, and 1, π/2. Finally, in step 3, we visualize the reflection. When we plot these new points and connect them with a smooth curve, the resulting graph is a perfect mirror image of the sine wave across the line y equals x. It is important to notice a fundamental shift here. The x-axis of the inverse function now represents the ratio, with values ranging between -1 and 1, while the y-axis now represents the angle, with values between -π/2 and π/2. Keep this distinction in mind, as in the next slide, we will discuss some common pitfalls, such as confusing this inverse function with a reciprocal. Common mistakes to avoid. Now that we have seen a practical example with the sine function, it is important to address some common pitfalls that students often encounter when graphing inverse functions. First, let's discuss the confusion between reciprocals and inverses. A very frequent error is assuming that the graph of f inverse of x is the same as 1 divided by f of x. Please be careful here. The graph of inverse sine of x is specifically the reflection of sine of x across the line y equals x. In contrast, if you take the reciprocal of the sine function, which is written as sine x to the power of -1, you get the cosecant function. This is a completely different curve characterized by vertical asymptotes, and it is not the same as the inverse sine function. Next, we must talk about the importance of domain restrictions. You might be tempted to reflect the entire infinite sine wave across the mirror line. However, as we discussed in the earlier sections, the full sine wave is not a one-to-one function. If you were to reflect the whole thing, the resulting curve would fail the vertical line test, meaning it would no longer be a function. Therefore, always remember to reflect only the restricted domain that ensures the function is bijective. Finally, be mindful of the mirror line you are using. When sketching your graph, ensure you are reflecting the curve across the line y equals x. It is a common mistake to accidentally reflect the graph across the x-axis or the y-axis, but doing so will not yield the inverse function. Always use the identity line as your axis of reflection. Key takeaways. To wrap up our session on the graphical representation of inverse functions, let's look at this summary table, which consolidates everything we have discussed in the previous slides. First, let's look at the coordinates. As we established in our second slide, the fundamental rule is a simple swap. If the original function, f, contains a point represented by x, y, then the inverse function, f inverse, will contain the point y, x next. We have the relationship between the domain and the range. This is a direct consequence of swapping our coordinates. The domain of the original function f becomes the range of the inverse function f inverse. Conversely, the range of the original function f becomes the domain of the inverse function f inverse. This is why, in our sine example, the range of values between -1 and 1 became the input, or domain, for the inverse sine function. Finally, let's review the geometry. While the original function is plotted as the original curve, the inverse function is always its mirror image. Specifically, it is the reflection of that original curve across the identity line, y equals x. By keeping these 4 key transitions in mind, you can easily derive or verify the graph of any inverse function, provided the original function is bijective.